Hi, I'm Colin O'Flynn, and I'm here to talk to you about low-cost body biasing injection attacks on WLCSP devices. All right, so there's a lot going on there in that title. What are we actually talking about here? Well, what we're talking about is something you might have noticed if you look at like fault injection papers, when they go over what are ways to inject faults. You enumerate through the various ways you can inject them, and the foremost obvious laser FI, right? We have quite a few different papers using that. We have some commercial tools available for it. Electromagnetic, same thing. There's several different tools, commercial and open source, as well as many papers showing it used in practice by different teams. And we go down the list: voltage fault injection. You have many vendors of the tools. You have many examples of it that stretch, back 20 years basically of doing voltage fault injection. Very active method, very useful. And finally, clock fault injection rate, same almost as voltage fault injection. It's been around for a while. It's used extensively in real life in academic publications. And it even goes back to the unloopers from smart cards. So there's tons of examples of all of these four ways. But these aren't the only ways to inject fault. There's another method that's called body biasing injection, BBI, that's frequently referenced. So you'll often see BBI listed as a way of injecting faults when people enumerate them. But when you look at who's actually done the work, what I sort of found was that it wasn't used in practice by other teams as often. And there was sort of an assumption here, perhaps, that it was related to the effects you were expected to get out of it and the actual cost of the equipment and setup. So that's what I began to investigate. Really quickly, body biasing injection, BBI, the idea of it is if you have your chip, so I've just taken an example of layers of a chip from Wikipedia and rotated it, so sorry the text is all upside down, but you basically have the backside of the chip here, and we put a probe on this, right, and so there's some silicon and stuff there. We inject a pulse, so a big voltage pulse, right? And it could be and it could be positive or negative, right? But it could be maybe a few hundred volts. So let's say 10 volts to 400 volts, something, depending on the device. And the idea is this is going to couple into the actual chip structure itself, right? So this is the basic idea of body biasing injection. So unlike EM, where we're coupling electromagnetically, we're actually positioning a probe over it and trying to either couple directly or maybe some capacitive level. But there's a way we're actually more directly coupling into the chip itself. And in the previous setup, so here were some images pulled from some of those previous papers I just referenced. And you can see basically there's a needle, right? So you have a micro probe on an XYZ stage. It's positioned over whatever the chip is. So here's a chip with the backside opened up of it, for example. We have a small probe. And to do this, right, there's a pulse generator. So this is an off-the-shelf pulse generator. They can get pretty high voltages, so it's a fairly expensive piece of gear, but it is, more or less off-the-shelf test equipment, so it's not crazy. But basically what you see here is that the cost of this is going to be probably similar to EMFI in reality, with the added step that all of these are using some processing to expose the backside of the die. So there's this additional step involved in BBI that you don't need with EMFI. EMFI is really nice because you typically don't have to do that exposing of the die. So to bypass the requirement to expose the die, what I looked at is using Wafer-Level Chip-Scale Packaging, or WLCSP. And so this has been shown before. There are several examples of this being used for BBI even, but I didn't see it used really in a sort of setting that was actually investigating how well you could apply it and what it sort of meant for the attacker or defender. So with WLCSP packaging, you more or less have the die itself, so it's more or less integrated into one package. The die backside is roughly exposed. And you can see here actual structures of the chip and stuff. I mean, if you take these and look at them under a microscope, it's very clear. You can actually see the chip structures from the underneath there. The reason the die backside might not be fully exposed is that there actually was an issue before with this. So in the Raspberry Pi 2, it had an issue where if you did a xenon strobe over it, you would actually see the device reset. So what this means is there might be some covering over the backside of the die that you can either scrape off. Occasionally there's like a bit of, so depending on the format of the chip, there might be a thin layer of encapsulate around it, right? It's nothing like a regular package, but it might need either a small amount of mechanical abrasion or some minor chemical abrasion to expose it. But it's still quite trivial to do. So in my case, mechanical worked, or even just acetone, right? So acetone at room temperature, remove that coating perfectly, or you just use an X-Acto knife and scrape it off. So very simple setup. And we can see WLCSP devices in real life anytime you need a small device, basically. But it is available, so both normal micros and secure micros use this package. So I'm actually using the STM in this work, 32F415. This series is used, and then this is the Wafer-Level Chip-Scale Package device. This series is used in some other work, so it's a good reference to compare to. So why BBI? We know some things about BBI that makes it nice. So from previous work, we know that there's some XY positioning capability. So we like that because we can target specific areas of the chip. We also hope that detectors for light or EM might not actually be tripped by BBI because the pulse is different, right? That's being injected. It doesn't have the same characteristics. So it may not actually trip detectors that are looking for light or EM fault injection. The risk of BBI, so it is a bit different. You can actually damage the IC. So here's proof of this. Here's a Vol blowing up a PS4 chip. So this is not a super cheap experiment to have this go wrong. And he has a little video with the magic smoke coming out of the device as he's trying BBI on this. So this actually works on, so this isn't a wafer-level chip-scale package, as you can see, but this is another common format where you have a BGA and there's something like, the wafer-level chip-scale package embedded onto it. And in this case, he's thinned the backside of the die a bit to make it more effective. But the point of that is that, you can get away without needing all of the chemicals to actually do this depackaging. So anything with this exposed backside makes us not need to use chemicals, right? So this is great because you don't have as much risk to you that things are going to go really badly. The other part that I'm going to introduce here, so this paper also introduces the idea of the injection tools for BBI being actually a lot cheaper. So much cheaper than laser for sure, and far cheaper than EMFI. Basically, maybe voltage glitch level, and potentially cheaper than that. The only real expense is if you do need an XYZ table, right? You can use a 3D printer and stuff like that is fairly common. But even some of the experiments I'm doing here, I'm not going to use an XY table, just to demonstrate that it is very possible. So the other issue with wafer-level chip-scale packaging is that they're very small. It's a very small grid, right? So it's like 0.4 millimeter or something between the balls. And so this is all open source, by the way, these target examples. What I've done is I've eliminated the need to use micro vias or need any or filled vias or things that are expensive if you're just doing prototype. So if you're doing production, it's not such a big deal, but if you're trying to experiment, right, you want to use the cheap services to make your life easier. And what I've done here as a test is I just don't have some of these balls, so there's no electrical connectivity. There's nothing that it solders to, and the solder mask sort of isolates it. So this is what I use for a lot of the demonstrations here. The basic idea we're going to use is use a transformer to generate our pulse. So we'll use a transformer that has, I'm arbitrarily choosing like a 1:10 ratio or something like that, right? So it works out to about that. And the idea being that if you insert like a 0 to 30 volt pulse, you'll hopefully get like at the output of here, right, a 0 to 300 volt. And of course it doesn't exactly work like that. But the basic idea is that by using a transformer, we can generate a cheap, or we can easily generate this low voltage pulse that then inserts a higher voltage pulse onto the backside of our die. So this is it. This is how we make BBI injection much more accessible. This is a schematic of the Rev 0 probe, basically. So this is what I call Rev 0. So the design files for this are up, but there's not much to it. Right, the only real trick is this transformer, which is custom wound, so I have the specifications for that. It's just a small piece of ferrite rod with, you know, something like 6 turns of this and then 60 turns of a thinner wire. So that gives us about our 1 to 10 winding ratio that we expect here. We then just charge up this capacitor bank to whatever voltage we want, and this generates our pulse here, right? A small pulse, and then we hopefully get a bigger pulse at the output. To use it, it looks something like this, right? So this is our custom wound transformer here. And you know, it's pretty messy. It's fine. It actually doesn't need to be done very well. It seems to work. So this is the one that was used in all the paper, right? So you can really see you can get away with a pretty messy setup. We have a probe, so I'm going to talk more about all the instrumentation that's only used for the paper. You don't really need this if you're doing, you know, the work as an attack, let's say. And you can see I just have a vise here. So in this case, I'm using a vise to just point at one specific part of the chip, and I sort of found that by moving around a bit. To drive this, I'm actually using a chip whisperer here. So this just generates like a glitch output. So the chip whisperer, as part of like any of the glitch logic, can generate a pulse. In this case, I use that pulse to drive the MOSFET that then inserts the glitch here. So you can use whatever method you want to generate the pulse. It just needs some sort of logic level pulse. So it's all pretty, you know, the requirements around this are pretty straightforward. You don't need $1,000 worth of equipment to make this $10 probe actually possible. You just need a power supply, right? I'm using a bench lab power supply. You could use like a really cheap LM317, anything like that. And you need the way to generate the glitch. So those are the only real hard requirements. We've done some additional characterization. So what I've done here is added, and this, you know, adds a little more cost. We have basically a high bandwidth current probe. So this Tektronix CT6 current probe is used to measure current, and normally you'd have a wire going through this hole. As it turns out, the probe perfectly fits through that. So we can actually measure the current that's being injected into the chip backside. So we can get a really good characterization of that. And we can measure the voltage. So we have a 100 to 1 passive scope probe just to measure the voltage at that point. So with these two things, we can actually see what's happening on the die backside in terms of the injected signal, right? So it ends up looking something like this. So what I have here at the bottom is this is the voltage, right? So the voltage that I've set as the input to my probe. So I've kind of added a little arrow here to make it clear. I'm measuring just whatever the input is. And I've chosen a point on the chip, right? So this is like this exact point right here. This was the setup tested with. And as I insert a given pulse, I measure the maximum current and the maximum voltage. And you can see there's sort of this generally linear relationship between the input voltage and both the current and voltage output, which is what you sort of expect. It's going to vary with changes to the impedance of the target backside, which means as I move the probe around, as I change the target, things like that. But you can see, you know, roughly you're getting up to like 150 to 175 volts, right? And about at peak, like a little over 800 milliamps. So it's not massive currents or voltages, which means this probe seems to be very reasonable for doing this. The other thing we can see is what is the resistance, right? So if you use a DMM, if you use a multimeter, it's like 200 kilo ohms. So if I put a multimeter on the backside and ground pin, it's like 200 kilo ohms. There's 220 maybe, I think in the paper it's more accurate. If I divide, right, if I pick a point here and say like divide whatever this voltage by current is, it works out to a lot closer to like 250 ohms, right? So it's either an AC impedance, might be one thing, because this is a pulse. Remember, I'm looking at the maximum voltage and current of a pulse going in, not of a constant voltage. It also might be a little related to the breakdown voltages. So I don't know if this is purely an AC impedance relationship here, or if it's the fact that, you know, this DC resistance is measured at like 2 volts, right? And this is measured at like 100 volts. So there could be some breakdown happening that's actually changing that. As an interesting note, if you blow up the devices, so which happens, they then afterwards show a very small resistance. So it does suggest there's actually some breakdown effect occurring here to me. Okay, so on to results. There's kind of a few different results to talk about. The first one is the loop. What we have for the loop is, in fact, 2 loops, so it's a lie. We have 2 loops here that are incrementing one variable in the inner loop as well as their outer loop counters. And all it looks for is it just looks for if that final loop count is wrong. If that final loop count is wrong, it means something corrupted, right? So we either corrupted one of the comparisons, we corrupted, when it's doing this register load back and forth to memory because these are declared volatile, it corrupted that. There's a lot of options for us to corrupt. So we expect this to be pretty vulnerable. And we expect to, really easily get glitches if this thing is working. And what we see is at the bottom here, we have the input voltage. So this is the DC voltage setting, right, that I've set to the probe. And then I tried different widths. And this is measured in cycles of the target device to be consistent with different running speeds. And I'm starting with a slow running target device. And you can actually see that there's pretty big ranges, right? So sort of one thing that what you expect as you have lower voltage, it takes wider pulses before you get effects, right? But at higher voltages, we're starting to get effects at narrower and narrower glitches. So that's sort of interesting. The other thing is that, so at each location, there's actually multiple attempts made. So the opacity of this is indicating how effective the glitch was. So you can download the full data sets to calculate this, but many of these points have like 100% successes. And you can see there's like huge swaths of areas, right, where we're getting really good successes without any reset. So the red X's are showing the reset locations. If I crank this up from 7.37 to 40 megahertz, what you can see is that we still get a lot of successes. It didn't search the whole area. So basically it did a search strategy that would increase the voltage like this, right? And if it saw a bunch of resets, it would just stop increasing it. And then it would use that as the new maximum. So you can see like a bunch of resets happened here and then it didn't search as far in the future. And that was just done for speed. You can see with this one, there's a lot more widths it's searching than the previous one. But you can still see, right, like even if there maybe were more areas that were giving successful, there's still really easy successes here. We can also look at what happens if we do XY positioning, an XY positioning solution here, right? So if we do an XY positioning solution, what you have is something like this. So there's an XY table. It scans over the surface of the device. And basically each of these red dots is a test. And there's like 2090 tests at each point. I'll talk about that in a second. It's a little bit misaligned from the grid. You don't want to hit the edge of the device because it actually breaks off really easily. And I just kind of eyeballed where my scan was going to take place on it. And anyway, it is what it is. It doesn't really affect it because all we wanted to see is how sensitive was the position, right? If I move a small amount, what does that actually mean in my results? And at each point, as I mentioned, we scan both the voltage and the glitch cycle. So lots of scanning happens at each point. And what you can see is, so this is the resets, this is the successes. It's sort of what we expect. Number one, there's some points that are pretty good, right? So like here, for example, there's 233 resets as well as 207 successes. Remember that this is a total between all voltage and width settings. So if we look back at this figure, for example, right? If you took this width along here, right, you would see that you have both successes and resets, at that same location, depending on the voltage setting for, in that case, for a fixed width, right? So that's why we have locations that have both successes and resets, because it's measuring a total. And we also see that it seems like there's some more sensitivity down in this area, than up here where there's really not a lot going on. We can also look at what the minimum voltage is before we get interesting results. So this I think starts to get a little more interesting because we're now narrowing down, what happens as we, change some of the settings. So the first thing is, when is a first glitch seen? So this is when we see any glitch at all. which means it might not be a reliable glitch. The second one is, when do we get a reliable glitch? So when do we get at least 10 glitches at this location? And what's the minimum voltage that we've reached that? Because we assume as we increase the voltage, as we saw before, right? As you increase the voltage, basically you go from 0, there's no effect, and eventually you either get glitches or nothing happens. And so you can see, for example, up in the corner, there's actually sort of interesting. You see these 3 locations where you do get glitches with sort of nothing in between them. So we can see there is quite a bit of spatial sensitivity here, it would seem. And this is reliable glitches we're getting, right? So it's not just that we happen to maybe get a fluke of some glitches at one location and none at the next. We also see some nice sensitivity down here. So if you look at this seems crazy. It's like 0.5 volt input. It's actually getting, some glitches at all. And on this one right here at a 0.5 volt input, it's getting repeated glitches. It's getting 10 glitches in a row at least. So you can see there's drastic differences in the sensitivity to whatever that glitch loop is doing. Remembering that the glitch loop could, right, if you glitch the SRAM, if you glitch the ALU or anything, you're going to see this. Yeah, so as I mentioned, the full data sets and some of the notebooks to generate this is available. I can't really, there's so many, there's so much in the data set, it's hard to show everything. What I really wanted to show is that the fact that it is very dependent on spatial position. There's an RSA example. So this was sort of in the original BBI paper. An example was done on an RSA classic CRT type implementation. Right, in the embed TLS implementation I'm testing, it actually does check if the return signature is valid. Claimed reason to be to match the original paper that had a single glitch. I don't want to compare a single and a double glitch. We removed that check, right? Of course, you might say that that's in fact because we're lazy, but I leave that to your discretion. It's more or less what you expect. So you saw it was a very reliable glitch with the loop. To confirm you get an exploitable P or Q with the RSA glitch works very well, right? So this is about 54% of the time. You do get an exploitable result, which means I recover P or Q when I run the attack. The other sort of interesting thing is briefly tested DFA on the AES, on the Hardware AES engine. And there's multiple responses you get, right? So you can get a lot of weird stuff like just key leakage. So some of these, like key leakage, partial plaintext leakage, are probably assumed to be that the engine didn't actually run, right? So if the engine doesn't run, you'll probably get something like this because it copied data in, never did anything with it, and then you copy data out. We also got some interesting looking output. So we classified that as something that wasn't obviously either, the input, the output, the key, or just constant zeros. So the interesting looking output was probably what would be most interesting to explore more. So we didn't push this to a full DFA attack, but we did look at where these happened. And for example, this is showing all the different results. In this case, the width is fixed. We're sweeping along in time where the glitch is inserted, and we're scanning the input voltage to increase it. Because the STM32F4, the engine leakage is known, we can do an attack on this to actually figure out when the hardware AES is running, not just when we're calling the routines. And this sort of confirms what we were guessing. So the key leakage stuff actually happens pretty early on, right? So when we see the key copied to the output, it happens if we insert a glitch early on in the system. When we see this interesting output is actually later on, sort of around the time where close to the last round leakage location. So this seems to be when the encryption is actually occurring, so during some of the rounds. There was no obvious fault model here though, so this was the issue. If you took the output and you reversed it back to compare the internal states, it never matched anything that I would expect. So it never matched the input, it never matched like an obvious corruption of the input or anything like that at any of the intermediate states. So it might be that, the key scheduling was scrambled. That would have explained this. It could be that there was some total garbage loaded. Unclear, but it is clear that we were getting interesting results out of this. The other sort of interesting thing we got was Flash being programmed to 0. So what I had seen was that, as I was running this, sometimes the device would stop responding, right? So the device would stop responding weird, and until you reprogrammed it, wouldn't work again. When I dumped the flash memory, I actually saw zeros at a location. So then this experiment here was done where the flash is erased, a bunch of glitches are inserted, and then the flash is read. And you can see different amounts of zero at the beginning. So here it's just like a few zeros, here it's a whole bunch of zeros, right? And it always kind of stops arbitrarily. It's not like one page that's set to 0 at a time. So the assumption here is we're tripping some programming routine, because remember this has a ROM bootloader. So it does have some ROM routines that would do like flash programming and things like that. So it's possible that's being tripped, right? Because it's always programming it to 0. We erase it to the FF state and then it programs it to 0. But it seemed like if we change the glitches to happen more frequently, the number of zeros was shorter. So it was a shorter 0 sequence than if we glitch slower, it would be like a longer 0, as if it was getting interrupted. We also saw some sort of physical damage. So on one device in particular was pretty interesting, because a small percentage of the bits would always read as 0 if you performed a chip erase. So if you chip erased everything to 1, a small percentage of them would read as 0, and it would vary every time you did the read. But it only happened on half of the flash. So for half of the flash, we got this. The other half worked perfectly. You could program the bits to 0 totally fine. It was just when you were trying to erase them. There was also no obvious damage in terms of excessive power consumption, right? So it might be that like maybe there's some minor damage to like the charge pump or control circuitry or something like that. A bunch of devices just were destroyed. So like, 2 or 3, not a huge number. They basically would get very hot and just didn't work. Interestingly, at least one of them kind of worked, right? So these are devices that are being done for power analysis. So they have this resistor in line. So it's going to limit a little bit how much current the device can take. And the devices still talked over the bootloader. They just couldn't do stuff like memory program or erase anymore. So they worked a little bit, but not fully. So I don't know if parts of them were damaged, parts of them were, being crowbarred or things like that. But yeah, that's a very fast summary to body biasing injection. Doing it at a really low cost using wafer-level chip-scale devices that makes this, I think, a lot more interesting because it's very accessible to anyone. And to improve that accessibility, all of the details are posted on this GitHub, which includes schematic, board layout, all the data sets I've used in the paper, a copy of the paper. So you can sort of, hopefully recreate it, expand on it, and try your own results. If you're interested in talking more about it, I actually set up a Discord, so sort of a chat server for this that's related to hardware security. So there's quite a few people there already. And if you do try it, feel free to let me know how it works. I'd love to hear about it. And hopefully you enjoyed learning about body biasing injection and how you can do it for low cost on many of these devices.